Hi, I'm Casson Crooker. I've worked in the game audio industry for over a decade as audio director at Harmonix, and now I'm the director of product development at THX. THX's mission is to provide consumers with the best entertainment experience possible. We got our start when our founder, George Lucas, wanted to provide a better cinematic experience. You might also know the iconic Deep Note trailer that continues to excite viewers around the globe. And for nearly 40 years, THX has continued to provide exceptional entertainment experiences to everyone, everywhere. Beyond cinema, THX provides the gold standard when it comes to audio and visual fidelity, known as THX certification. THX certified products undergo hundreds of tests, which ensures a great audio-visual experience out of the box. We also have innovative products such as our award-winning THX AAA technology. And of course, we also have what we're here to talk about today, our immersive THX spatial audio technology. Our innovative spatial audio solution is in products like headsets, mobile devices, and PCs. But to elevate gameplay with more authenticity and detailed soundscapes, we've developed a suite of THX spatial audio game plugins with our friends at VisiSonics. These plugins can be incorporated directly into the game's design and architecture and are compatible with Unity, Unreal, and Wwise, as well as bespoke game engines. And, as a paid upgrade, developers can integrate Personal HRTF into their games, resulting in an audio experience that reflects how individuals perceive sound in the real world. Taking a closer look into how the plugins work and how the entire process works, I'd like to introduce Michael Henin, VP of Product at VisiSonics. Michael, take it away.
Thanks for the intro, Casson. Hi, everyone. My name is Mike Henin, and I'm VP of Product at VisiSonics. Thanks for being here. VisiSonics was founded by leading experts in spatial audio perception, propagation, and capture of sound, drawing from research and development at the University of Maryland Computer Science Department. As mentioned by Casson earlier, THX and VisiSonics have partnered together on the THX Spatial Audio plugins for gaming, featuring a hybrid approach to spatialization. They're able to dynamically render both object-based audio and ambisonics in real time. Let's quickly go over what object and ambisonics rendering is, after which we'll discuss how a hybrid approach is beneficial to game developers. As we all know, object-based rendering coupled with physics-based room simulation provides the highest fidelity 3D spatial audio. While this is the preferred way to render, there are both creative and platform choices that often require ambisonics rendering as well. For example, when authoring for mobile platforms due to their limited audio processing capabilities, or when wanting to use diffuse ambient background audio as a sound bed in conjunction with accurate object rendering. With THX Spatial Audio, it's possible to have your proverbial cake and eat it too by allowing for both dynamic, object-based, and ambisonics rendering together. Let's go over the differences between object-based rendering versus ambisonics first, as a quick refresher. All formats, whether object-based or ambisonics, seek to create the correct audio experience at the listener's location. Object-based format encodes the following: the source sounds, the listening space, and the locations in the room relative to the listener, using an engine to propagate the sound from the source to the ears of the listener. This includes the direct path, reflections, reverb tail, and their interaction with HRTFs. Here are the pros of object-based rendering. Object-based rendering can achieve extreme reality since it simulates what actually happens using physics. Also can be easily customized to real spaces and can be customized to individuals via their HRTFs. Now the cons are the following. As the number of sources and reflections increase, the processing costs go up. Also, they tend to use non-standard formats. Object stems and associated metadata are typically proprietary, although this is part of an emerging standard such as MPEG-I, for example. To hear the full 3D effect, be sure to put on headphones for the remainder of this presentation. Ambisonics represent audio near the listener as a summation of spatially varying functions. Ideally, a sum of an infinite series of this family of functions known as spherical harmonics. 4 members of this family used represent first-order ambisonics. 9 members of this family used are second-order ambisonics. 16 members of this family used are third-order ambisonics, and so on and so forth, up to 7th order, which is 64 members. Now, the pros of ambisonics are the following. Number of channels required for rendering stays the same for a given order. For example, 4, 9, 16, etc. for either first, second, third, or so on. First-order ambisonics has become a relative standard. For example, it's used in YouTube, Facebook, and others, and is supported in MPEG-H, for example. Cons. The cons of ambisonics are that while you're able to capture sound variation around the listener, it's not quite able to deliver a crisp source image. And lastly, they tend to somewhat be hacky when it comes to delivering a notion of distance or reverb. Now, let's talk about objects versus ambisonics rendering. Object-based rendering does not use spherical harmonics. THX Spatial audio, for example, represents sounds as waves coming from a collection of sound objects. Now, this method for object-based rendering is essentially a brute force number of waves convolved with HRTFs to create a sound field. For example, the THX Spatial audio plugin typically has hundreds of source directions and HRTFs in a rectangular configuration. Compare that with only 8 HRTFs with first-order ambisonics. As a result, object-based rendering does render positional cues much more accurately than ambisonics. However, the trade-off here is processing. With ambisonics, as the number of sources in an environment grows, the ambisonics representation that is centered around a user has the same size. This is very beneficial. This certainty when it comes to the size allows for convenient storage of the sound in a scene, for example, using just 4 channels in the case of first order, and is easy to distribute as a single file with a video, as we see with the adoption of first order ambisonics in YouTube and in Facebook. Next, we'll show how to set up both object-based and ambisonics audio using the THX Spatial audio plugin for Unity. After that, we'll show how our HRTF personalization pipeline can inject your very own personalized HRTF in runtime. For this particular presentation, we're going to demonstrate the Unity plugin. First, we'll need to import the THX Spatial Audio Unity package into the scene. Next, we're going to set up the Unity scene to ensure THX Spatial Audio will be enabled by making sure the desired sample rate is set, our Spatializer plugin and Ambisonics decoder are selected. Once the Unity plugin is fully enabled, you can see that all the necessary game objects are available. We're going to be focusing on the audio source and virtual room objects for this walkthrough. Before we continue, we'll need to enable the main camera to use the THX Spatial Audio Listener component. Now, let's go ahead and create a simple object in Unity. Let's go with a sphere. Next, we're going to add an audio source component to that sphere so that it can emit sound in 3D. The THX Spatial audio source component has all kinds of powerful parameters to adjust as needed. Let's attach an audio clip to this object to hear it emit sound. We can move it around in 3D space to test how it sounds. Now that we have an object emitting a direct path to the listener, let's add reverb reflections to really make it sound even more realistic. We do this by simply adding a virtual room around the object. The virtual room can be fully customized by changing the material properties of the room, so it can be very reflective, very absorptive, or however you like. We have pre-made virtual room presets for simple use, or for more advanced development, a developer can customize each surface material to their liking. Here's what the default room sounds like. Notice how the reflections add so much more realism to the sound. It's almost like being there. Now that we demonstrated how to play back object-based audio using THX Spatial Audio, we'll now show you how to set up THX Spatial Audio to play back using Ambionics rendering. Since we've already imported the THX Spatial plugin package, let's verify the following in the Edit menu by going to Edit, Project Settings, and there we're going to make sure that the Spatializer plugin, as well as the Ambionics decoder, have THX Spatial Audio selected. Also, make sure the plugin is set to 44/100 for the sample rate. Next, let's select the main camera in the hierarchy window. While there, we're going to add a component. Search for THX Spatial Audio, add the THX Spatial Audio listener. The audio listener defaults to Ambionics, so we can leave these settings as is. Next, we're going to add an object, in this case, a sphere. On that object, we're going to add an audio source by going to the Objects Inspector window and adding a THX Spatial Audio source. Now, go ahead and select an audio clip to add to the source for playback. We're going to use a water type sound. You can see in the inspector, we have the ability to choose Object, Ambionics, or Combined. So you can be in Object rendering only, Ambionics rendering only, or Combined, meaning the object can switch between Object or Ambionics rendering, for example, based on distance. One thing we need to do is find the audio source by going to the Assets folder to make sure that your audio source is set to Ambionics playback. You do this by finding the audio file, go to the inspector, and select Ambionics. This is needed in order to make sure the sound playback as Ambionics and select Apply. Now, let's go back to the sphere object and let's go to the audio properties under the Audio Source Inspector window and make sure the audio clip is the audio file you want to play. Then, make sure we're in Ambionics mode, playback mode. Now, we can hear the Ambionics playback by pressing play. I'll move the object around the listener so you can hear the sound move around you. Again, make sure you have headphones on to hear the playback in 3D. Well, that's the basics of the THX Spatial Audio for game developers. While this demo showed our Unity plugin, the Wwise and Unreal plugins are also super friendly to work with, allowing developers to focus on creating content. Before we showcase the THX Spatial Audio Personalized HRTF capture and backend process and how it integrates with the plugin in addition to working in runtime, we're going to go over essential concepts and review the technology behind personalizing HRTFs. It's well understood that HRTFs are the key to rendering 3D spatial audio, a subject that's actually been covered a lot here at GameSoundCon. In fact, VisiSonics gave a talk 4 years ago on the subject. When it comes to HRTFs, there are a few important things to remember. An HRTF represents a sampled filter of a particular point in space relative to the listener. When you capture hundreds of these locations all around the listener, you can create a full 360-degree sound field around the listener. Now, the HRTF is only the direct path. For the most spatially immersive experience, the BRIR, or binaural room impulse response, which actually includes an HRTF and the corresponding reflections in an environment, also needs to be calculated and processed for the best effect. So when we have these sampled locations as well as reflections that are calculated in real time all around the listener, a sound can then be moved around dynamically, being processed with each corresponding location within the modeled environment or room to create an aural illusion of a full 3D effect for listeners. Ever wonder what an HRTF looks like? Well, here's what they look like. Again, as we discussed just a moment ago, that this HRTF only reflects the direct path only, with no environmental reflections, which improve localization. Why? Because humans typically listen to sound within an environment, not within an anechoic chamber. Typically, 3D spatial audio that you hear out there use what are called generalized HRTFs, meaning it's a general filter set which can work for most people, but not all. Essentially, you're listening through someone else's ears when you're using a generalized HRTF. Over at Microsoft Research, Ivan Tashev states that, quote, a one-size-fits-all solution or some kind of generic filter does not satisfy around 1/2 of the population of the Earth. So why don't a generalized HRTF work for everyone? Based on what Ivan Tashev stated, that's actually a lot of people. Well, it's simple, really. People have unique ears. They also have a different head shape and different shape of their torso. So no two people have the same features from ears, head, and torso. So if the ear and body shapes are different, then the properties of the scattered waves are different. And HRTFs will be very individualized. So individualized HRTFs create proper spatial audio. For example, research shows that elevation as well as frontal perception are greatly improved when using personalized HRTFs. Look at these two diagrams of two different individual HRTFs. Notice how the frequency response is really, really different between the two. Why is that? Well, that's because the ear shape and all the little nooks and crannies for each ear are different for each set of ears per individual. And basically what this means is the sound scattering and bouncing around these little nooks and crannies arrive into the ear canal differently for each person. And that's what results in a different frequency response. Now, let's talk about how HRTFs are created. Well, there are 3 accurate methods being utilized today. 1, captured. 2, computed. And 3, matched. Capturing HRTFs are typically performed with 2 methods. The first method uses a speaker array. There are a few approaches, but in general, the idea is to emit reference tones around the user who's wearing microphones in each ear, capturing each speaker location in space in an anechoic chamber. The process is typically slow, anywhere from hours to about 10 to 20 minutes, and only gives you a relatively small number of filters, less than 100, for example, because there aren't that many speakers being used. The second method I'd like to discuss is using a microphone array. Now, VisiSonics actually patented a really unique method that uses what's known as the fast reciprocal method that uses an array of microphones as opposed to an array of speakers all around the listener. So this approach essentially reverses sound coming, instead of sound arriving the ear, it's actually the sound coming from the ear out to a room or a measurement system that has a bunch of microphones all around it. This approach uses microspeakers placed in the ears of the listener, which point out, and the reference tones are captured within a small room or booth with an array of around 512 microphones all at once, So this method allows for HRTFs to be captured in seconds. This method uses the principle of Helmholtz reciprocity, which states that if you place a sound source and microphone in 2 points in space, record or measure the signal, and if you swap those locations, you get the exact same recording or measurement. This system is currently deployed at 2 U.S. Veterans Affairs or VA centers to help soldiers suffering from combat-related blindness to learn how to use sound to navigate the world in a safe lab environment. This method is very important for VisiSonics, actually, because it allows us to build a very large database. In fact, we receive funding from the National Science Foundation, NSF, to give freebies to students at the University of Maryland for them to get measured, helping VisiSonics build one of the largest private databases of HRTFs in the world. Next are computed HRTFs. Computed HRTFs actually yield very accurate results similar to the capturing methods above. And typically they use a scanned ear and head and which produce a 3D mesh. Now, once a clean mesh is scanned of the ear and head, then an HRTF can be generated by simulating sound waves physically scattering off of the mesh. Now, this uses a simulation within the cloud that once took hours, but VisiSonics has actually developed technology that reduces this to minutes. Lastly, we're going to discuss matching HRTFs using photos from a database. It is this approach that's being currently utilized with THX Spatial Audio for their individualized or personalized HRTF process. The idea is to leverage a very large database of storage images and HRTFs, then take photos of the ears along with the sizes of the head for interoral time delay or ITD, and then using machine learning and AI, we're able to find the closest match HRTFs using landmarks that are pointed on each ear. Here's the diagram of the process. Using any of these methods mentioned above, we're able to take the personalized HRTF and inject it into the plugin so that a player or user can use that HRTF to improve their overall sense of immersion, situational awareness, and reaction time. And again, the process being used by THX currently for the THX Spatial Audio personalized HRTF process uses the third process mentioned, which is the HRTF matching using photos from our VisiSonics database. Now, let's walk through the HRTF capture process by using an app co-developed by THX and VisiSonics called THX HRTF Creator. For this demo, we'll be using the Windows version of THX HRTF Creator. Now, let's walk through the HRTF capture process. First, the user will run the executable for the HRTF Creator app. Once the application is open, the user will simply follow the prompts. First step is to take a photo of the left ear by following the arrow prompt on screen pointing which way to turn. You do this by turning your head approximately 90 degrees away from the screen. Once you're in position and perpendicular to the screen, press the space bar. Once the photo is taken, you'll be prompted to crop the image around the whole ear. It is important to get the whole ear and ensuring that the ear is cropped properly. Now, before you move forward, examine the photo and make sure it's correctly cropped. And also, if you do not like the photo, for example, if it's too grainy or not cropped properly, you can press retake. Now, the next thing to do is to take a photo of your right ear. Again, turning your head 90 degrees in the direction of the arrow. Now, once you're in position, again, being perpendicular to the screen, press the space bar and the photo will be taken. Once the photo of the right ear is taken, again, ensure that your right ear is cropped properly. And also, again, if you do not like the photo, if it's too grainy and or not cropped properly, you can press retake. Once both photos are taken, you have the opportunity to perform a final examination of the photos. If the photos are too grainy or not cropped properly, you can repeat the process easily. One way to deal with the grainy images, if you do get them, is to actually add more light, preferably close to your head or ears. Now, once the photos have been finally examined, you simply submit the photos by hitting upload. Now, when you submit the images by pressing upload, the images for both the left and right ear are sent through the internet to the cloud. They are then received by our cloud server that performs the HRTF matching using a machine learning algorithm developed by VisiSonics. Now, once a best match is found, it becomes available on the server in the form of a URL. That URL can be retrieved in the form of a URL link or in the form of a QR code that can be used as well. Finally, we're now going to demonstrate how you can inject this newly generated HRTF into Unity or running inside of a runtime game. Setting up the THX Spatial Audio plugin to inject personalized HRTFs is super easy. If you go to the THX Spatial Audio Listener component, you'll see an arrow named 3D Sound Advanced Settings, which has a checkbox parameter named Expose Personalized HRTF and Build. When this parameter is checked, the code in the component audio listener then allows the loading of personalized HRTFs that have already been downloaded locally. Now, it's up to the developer to fetch the HRTF ahead of time in whatever manner they choose, as mentioned previously, in the form of a URL, QR code, etc. But what this parameter does is allow an HRTF to be loaded from any directory that the developer codes in. Another thing that developers are able to do is to expose a custom user interface with the ability to switch HRTFs. We support this by the development of an API that allows you to fetch and download HRTFs from the THX server. Shown here is an example user interface that allows you to enter a URL, where the generated personalized HRTF is stored on the THX server, which is then fetched and injected into the THX Spatial Audio plugin to be used in runtime. The HRTF is stored and read from whatever directory the developer chooses. Of course, developers can use the API and develop their very own user interface to expose the entry of a URL to be consistent with the overall UI look and feel of the game or app. The last thing we're going to demonstrate is switching between a generic and personalized HRTF in real time using one of the earlier demos that we shown earlier, except showing HRTFs being switched. Again, this demo requires the use of headphones, and when you do listen closely to the differences between the generic and personalized HRTF. Keep in mind, this particular personalized HRTF may sound off to you, maybe even the generic as well, since after all, you are literally listening through someone else's ears, in this case, mine. Hey, I'm back. Well, folks, that concludes our presentation of the plugins and personalized HRTFs. Next, I'm going to pass it off to Casson.
Thanks, Mike, and thank you for listening to our presentation. If you'd like to sign up and learn more about the THX Spatial Audio game plugins, please visit the link that's included in the video description down below.